Hello, hope you can all hear me. So I'm a postgraduate research student at Cardiff University in the UK. My background is in astronomy, but now I've kind of taken the education route and basically looking at how we can use the Fox Telescope network and the LCO network to encourage engagement in physics, particularly with girls, because it's a big problem in the UK as it is all throughout the world, really. So I'm just going to tell you basically a bit about the resources that I've produced and what I'm doing with the Fox Telescope and how I'm actually going to look at the engagement that they have and how effective these materials are and whether we're just wasting our time using these telescopes. So I realize this is all probably very familiar to you because it's pretty consistent throughout the world. But yeah, everybody just doesn't really like physics. Unfortunately, it's the least popular out of the three sciences. The entries in A-level has dropped. In the UK in 2004, the government were like, oh, we need more students to take physics, chemistry and maths. They kind of set a target for by 2014, we'll get the numbers up. And to be fair to them, they did. And then since 2014, it's just gone straight back down for physics and chemistry. Maths is still going up, but and we've also seen declines in higher education as well. So science of the core subjects in GCSE, which is what exams we do when we're 15, 16 at school. Science, in comparison to maths and English, it's the lowest achieving in terms of A star to C grades. But for the individual sciences, it's actually the highest grades, which you can see here, which is actually really bizarre because when you speak to students and you say, why don't you like physics? A lot of the time it's because it's really hard. But this doesn't translate into A-level. So by the time we get to A-level, physics then just completely drops and it's actually the lowest achieving A star to C grade. And again, you're probably all aware of the gender differences. It's been largely unchanged in the past 2 decades or so. Girls just have a really negative perception of physics. It doesn't interest them in the slightest, but they actually perform a lot better than the boys in the UK. And even still, they're so much less confident than the boys, even though the figures show that they're actually much better. And they're also a lot more likely to go on to higher education. So that's quite interesting to see. So I realize I'm preaching to the choir here a bit, but space is a great topic to engage students with. And it's kind of, apparently it's the sexy side of science. And although girls kind of tend to leanate towards more health-focused subjects, areas of science and things more personally related to them, and boys seem to go towards more mechanical, electricity, stuff like that. There's lots of studies that show everybody finds space interesting. So it's a good kind of point of engagement to use to get the uptake. Some studies have even actually showed even these students that are like, no, I have no interest in science at all, I can't stand it. When they're then asked about astronomy and space, they actually become quite animated, and yeah, that's always a point of interest. So I feel like that's a good way, a good route in. So I'm going to tell you a bit about how we've kind of tried to buy into that and the resources that I've written and produced, and how, again, Fraser mentioned that we try and use inquiry. So we're not just getting students to do the physics and the maths, we're kind of getting them to build up their skills, make their own investigations that will be useful for them, whatever kind of career path they take. So we have a series of resources. Not all of them use robotic telescopes, but I'm just going to, for obvious reasons, talk about those ones. So one of our activities is based on the Hertzsprung-Russell diagram. We actually have 2 versions of this. You can do it using computers, or for those teachers who are absolutely terrified, we have like a classroom-based version as well. So for the computer-based version, they use the telescope network, they observe an open cluster, and they produce their own color magnitude diagram. This all comes up in their curriculum, so they have to identify main sequence stars, red giants. So it's a good way for them to actually take these images themselves and see how we find this kind of data. But we also have a classroom version, which is essentially every student is given a card with a star on it, with a temperature and its luminosity, and a bit of string, and they have to basically produce an axis and create their own Hertzsprung-Russell diagram. Which works quite well in just a lot of problems that students have in the UK is with graph plotting and extracting data from it. So it's actually quite a nice way to work backwards and get them to put the data onto the graph and figure it out that way. The other thing we have is we look at the Hubble expansion. I appreciate that's 15 to 18-year-olds, that's quite a big age range, but this one is highly differentiated. So we can, if you want, you could do this activity in one lesson, or you could do it as like a long-term research project with kind of higher ability students or doing extracurricular activities. Basically what we do is we provide a data set, several data sets of type 1A supernovae. They're just given the photometric data, and then they have to produce the light curve themselves, from which they identify the peak magnitude. Then they can either create their own Excel spreadsheet themselves, or use here's the one I prepared earlier, that will calculate the distance modulus for them. Sometimes it comes up in some exam boards in the UK and not others, so it's kind of how much you want to throw them at it. And then what we get them to do is, once they've got the distance calculated, we get them to look up the radial velocity of the host galaxy of where the supernova targets are. So we get them to use a SIMBAD astronomical database. So they're kind of getting a bit of practice of doing some own, like going into databases, searching for relevant data. And then they create their own Hubble plot here. This is an example of what students have produced. And then just by calculating the gradient, they get the Hubble's constant, and they can then use that to calculate the age of the universe. So a lot of the time teachers are like, oh yeah, we just kind of show them this graph and explain this is Hubble. And kids don't really have a clue what they're actually looking at. So it's quite nice for them to actually go right back to the start and get all the data for themselves. That is the kind of pre-packaged version. It's all there ready to go off the shelf. But if you want to take it a bit beyond that, if you have a bit more time, or you have some students that are really good, we have our Adopt a Supernova scheme. So we've teamed up with the Gaia Alerts team at Cambridge University. So Gaia's main mission is producing the most precise 3D map of the Milky Way, but it's also detecting a lot of transient objects. So what we're basically offering to schools is they can kind of be one of the first people to follow up an observation of a newly discovered supernova, which is quite a big deal. And if they manage to get it pre-peak and they get some good comparison stars, then they could actually add their data points and their observations. They can track it over a month or so using the telescope network, and then they can add all their data points to their Hubble plots. So it's quite a big deal, I think, for them if they're taking their own measurements and using their own data to calculate the expansion of the universe. It's quite impressive for high school students. So we obviously need to provide quite a bit of background information for that. So they're all designed as teacher guides. So they're written for the teacher, because we suspect most physics teachers don't have that much background in astronomy itself. So we not only provide pre-packaged data sets and obviously access to the telescopes, but we have instruction guides, so for using how to do photometry on a number of different programs. Salsa J and Macaulay I have chosen just because they're free. Salsa J is also Windows and Mac driven, and as we do quite a bit with schools throughout Europe, it's multilingual, so it's just easy from that point of view. We also provide some background information, so things like photometry isn't something that comes up in the curriculum, so it's just to kind of give them an idea of what's going on, and then just some like quick quizzes to, if they want to go beyond it. They don't need all that to do the investigations, but it's basically, if a student asks a really weird question to one of the teachers, the answer should be in there somewhere. But obviously, I'm a PhD student and I want to see how this actually has an effect and if what we're doing is actually useful. So Fox Telescope's been running since 2004, but we've never actually looked at, other than anecdotal and seeing the work they've produced, we've never actually seen if it's had any impact on their engagement. Did they actually enjoy doing it, or are we just wasting our time and boring them to death? But hopefully not. So these are kind of some of the things that I'm trying to look at and trying to find out whether astronomy is exciting and engaging. Do they like doing the computer-based stuff, or would they rather do things just like producing the classroom Hertzsprung-Russell diagram? How does it compare with just a normal physics lesson? And is there any differences across gender like we usually see in regular lessons? And then also just how much support do the teachers require? So in order for them to implement it and for them to feel confident and for them to come back to us and use it with different classes, how much support do we need to provide? So I'm looking into this on a multiple case study basis. So I'm not actually looking at large numbers. I'm looking to go into about 10 schools and kind of work with them over a couple of lessons and kind of see exactly what's going on. So I'm using mixed methods. questionnaires, which if you've seen the posters, you'll see our lovely questionnaire, which I won't talk about too much. And then classroom observations and focus groups. It is sequential, so the focus groups I haven't actually written yet because those are to be guided by whatever comes to light in the questionnaires and the observations. So anything that comes up like, oh, that's a bit weird or that's interesting, those are then followed up to see kind of what's going on there. So there is more of a qualitative focus to the research. So yeah, I won't say too much about the questionnaire because there's a big poster upstairs which I'd like somebody to come and talk to me about at some point. But it's basically just an attitude questionnaire that's made up of Likert scales that asks about these several different areas. So it kind of gives you an idea of what experiences they're having. And the interest in astronomy and space science one is one that Michael has recently developed and we've recently validated. So we know that it works, we know that it measures attitude. The observation protocol I had quite a lot of difficulty with. I was looking for any existing ones that I could use, but a lot of them, they're mostly teacher focused or look at teacher and student interactions, and they're essentially just a checklist of anything that kind of went on. I wanted to kind of get a better idea of the actual behavior and how students engage, how do they then communicate. So what the teacher is doing and the actual activity itself is kind of irrelevant. It's more just kind of how the students themselves respond to it and kind of what communication they make with each other and with the resources themselves. So I do talk to them throughout the lessons while they're there and figure out what they're doing and what their thought processes are along the way. So most of the data I'm collecting will be the next academic year, but I do have some preliminary results so far. So I've got about 70 students over about 4 schools that I've been into so far. And they actually on the pre-test, they do see physics as quite interesting. It's just not interesting enough to take it any further than GCSE level. There is, of course, significant gender differences in the pre-test. So this is just useful for me to see that, yeah, these students are kind of representative. They're still doing everything that we would expect to see. And so far, we have seen higher enjoyment on the post-test, which is promising from my point of view as well. One student actually said, oh, so I can do science. And I was like, oh my God, this is like what you just dream of in a thesis for somebody to say at some point. I've also not been into 2 classrooms where they've delivered the resources in the exact same way. So each teacher gets the same package of material and nobody delivers it in the same way, which is really interesting to see as well. I've actually seen some reverse behavior. So I'll go and observe the lessons a few weeks before, just their everyday physics lessons, just to kind of get a sense of the students. And then I'll go in and observe them using the resources. And I've been in classrooms where the girls are just having absolutely none of it. The boys are kind of just getting on with things. And I was like, oh, this is a mess. And then I went in when they were using my material and it had completely reversed and the guys weren't really that interested and the girls were really getting engaged. So that was really nice to see. There's lots of different interactions as well, depending on the gender of the teacher and the gender of the students, which is quite interesting. Males are more confident in their ability, even when I'll ask them a question and they'll answer so confident in it and they might be wrong. And then I'll ask a girl and they'll kind of answer it with a question, kind of, I think it's this, and they'll be right. And it's really frustrating. And girls are more likely to follow the instructions and check that they're doing things right, whereas guys are like, no, I don't want instructions. They just dive right in. So I guess they're kind of the more natural inquirers, which I'm not sure if that's good or bad. So basically the next steps, so now I need to look at kind of designing the focus groups. Some things have come up which I wasn't expecting or I found interesting, so I want to probe that a bit more, because although the questionnaires provide a great overview and summary of what's going on, the engagement and stuff, I don't just want to know oh, did they enjoy it, did it work? I want to know why, what it was about it, what kind of processes happened along the way, what were their experiences. And then are there any differences across different kind of groups? Free school meal eligibility, so people from different backgrounds. Basically what makes a good resource, essentially. So yes, I'll shut up now. Thank you.
Very much. Any questions?
That's really impressive. I think we need more of this in our group to help market ourselves. Now, were you the teacher for these, or did you have a teacher?
No, yeah, they're written so for the teacher. So I try and I meet the teacher beforehand and kind of talk them through the materials, and then usually they deliver them to the class. I'll be there to observe anyway, so if anything, they're like, I don't know.
Is there a strong teacher effect?
No, I actually really struggled with getting teachers to sign up, because they're just like, no, we don't want to do anything that isn't day to day. So I've had a few guys, like within the kind of science department in the government and stuff, that have got me into school, so where they just kind of have to, the teacher's like, yeah, we kind of have to do what we said, so they're not even all completely willing teachers, which has actually been really good. But yeah, I've only been in one case where they were like, are you happy to deliver them? Which I will, but usually the teacher is happy to once I've walked them through. Yeah.
I was just wondering if you had, I didn't quite catch whether you said they're working individually or in groups, but what I was wondering about are the gender breakdowns, and if you see differences, whether it's like an all-female group, all-male group, a mixed group, in terms of pre-post successes or anything.
So in terms of how they work in groups, so I leave that. Yeah, I leave that up to the teacher. I say you can do it. They can do it as an independent work, or they can do it in groups. They tend to do it in pairs, and yeah, it will be girls together and boys together. And then they just have a questionnaire to fill out. They don't do that in groups, they're all just given an individual questionnaire. But yeah, it is just really weird how you see different interactions among the genders, and the pre-test and the post-test is a lot different. And the behaviour is always a lot different between the males and females.
Sorry, real quick. I mean, would you say there's any support for saying that let's have an all-girl group work on this project? Is that encouraging?
I think it actually is, mostly for the confidence reasons. Girls are less confident than guys, and they don't see it as a female subject. So I think if it's an all-girl, like when it's an all-girls school, they do better in physics, because it's kind of like there's less competition, and like they're not being kind of outshone, or they don't think they're being outshone by the boys. And I've also seen this is just what I've seen, I know that it doesn't happen everywhere, but I've also seen male teachers often undermine female students, and if they do something good, they're like, oh, you actually, but when it is female teachers, then it's a different relationship, which is quite frustrating, but interesting at the same time.